Okay, it's the second second topic of chapter 11 on PID motion control. Okay, the section 11.3, motion control with velocity input. Okay, in the case of the industrial robot system, all the amplifiers are placed in the velocity control mode. In that case, we cannot control the torque or force. Only we can apply the PWM using for the desired velocity. So the velocity input can be allowed to insert the amplifier. Okay, so in this case, we should design the velocity. Okay, the velocity will be applied in the form of electric voltage. So you should know that the most industrial robot system are using this kind of velocity input. Okay. Nowadays, we are applying the electric current to make the joint torque. This kind of robot system is different from the industrial robot system. So now we will call it as a cooperative robot, cobot. Cobot is the different terminology from the industrial robot. Okay? In the case of the cobot, the control input will be the joint torque in the form of electric current. This topic, the velocity input case, most industrial robot system allows to insert the voltage input to make the velocity. Okay? Both concepts are totally different. Okay, there are two kinds of control input. The first one, velocity control. The second one, torque control. We will deal with this concept. Next topic will be the torque control. Okay. The joint velocity will be commanded when maybe you are using the stepping motor. You just assign the PWM or number of the pulse. It will correspond to the velocity of a stepping motor. On the other hand, the motor amplifier is set for the electric control mode. Then the control input will be the velocity or electric voltage. So at that time, the amplifier will generate the velocity of the electric motor. Long time ago, we have used this concept. Okay, this velocity control mode. Okay, but now the many kinds of robot system has adopted the joint torque control mode. So in our lab we have many the cobot robot systems instead of electric industrial robot. Okay, we will assume that there is direct control of joint velocity instead of joint control. Okay, joint velocity will be the control input. Okay, and motion control task can be expressed in the joint space or task space. Okay, in the case of joint space, it's not difficult, but in the case of the task space, we will use the twist concept and also joint map to make the error and task space error. Okay. Motion control of a single joint. As mentioned before, the theta dot is the control input. After determining the theta dot, we will make the PWM or the number of pulses to corresponding to the theta dot will be assigned to the motor amplifier. Motor amplifier will make the joint velocity, joint speed corresponding to the theta dot. So now the commanded velocity will be the theta dot. It's not torque. Okay, so let's assume that the desired velocity is assigned as a feedforward term. Is it right? There is no feedback in here. Zeta dot is given in advance by the user, and then it will assigned according to the time progress. So it is called as open loop control because there is no feedback, and feedforward control. Those are the same concept. Because no feedback, sensor data are isn't used to implement. It's needed to implement. I'm sorry, noise here. Okay, but if you use the velocity control mode using the feedforward control only, maybe the error will be accumulated because no feedback. The actual position is not reflected in the control input. So I think the error will be diverged according to the time progress. So the alternative strategy to measure and reflect the actual position of each joint continually and implement feedback control. So I think it's possible to add here proportional gain and zeta desired minus zeta. Like this, we can add proportional control. Okay, so now we will use feedforward plus feedback control. Okay, feedforward plus feedback. Actually, it is corresponding to the proportional control. Okay, in the textbook, the zeta dot desired is ignored, but I'd like to recommend you to use this feedforward plus feedback. It will show the better performance in the control system. Okay, the Kp should be larger than the 0 to guarantee the stability. Okay, as mentioned before, it would be preferable to use our knowledge of desired trajectory, zeta desired function of time, to initiate motion before any error accumulate. Okay, this control is called as proportional or P control because it creates the corrective control proportional to the position error. Okay? On the other hand, this proportional control gain Kp acts like virtual spring. So if we assign some robot is given, and then the target desired trajectory is given, at that time it is if you assign this proportional control, it corresponding to assigning the spring, okay, spring to make the desired motion. Okay, the spring constant is very big. I think the very stiff motion will be generated from here. Okay, the spring, the virtual spring. It is corresponding to the spring constant. Okay, let's assume that. Let's analyze the error. For the analysis of aerodynamics, we will consider error dot. Error dot is corresponding to the zeta desired dot minus zeta dot. And then the control law zeta dot will be assigned here for the analysis. So this term is inserted here. Then zeta desired dot will be cancelled each other. Then minus Kp will appear. Then we have first order differential equation. Okay? Maybe you are very good at this kind of equation. In here, the time constant will be the 1 over Kp. Okay, from here we can know that if we assign the big Kp, the time constant will be very small. It implies fast response appear. Is it right? And then the 0 steady state error, no overshoot in the case of the first order. As mentioned before, 2 times settling error, settling time. Okay, if the initial condition is given by the 1, then the 2%, 0.02, this time will be actual value will be the 3.91 tau. Okay, but it is approximately 4 tau. So tau is given by the 1 over kp. So kp over 4 will be the settling time. Okay. In other words, if you choose the big kp, you will have the faster response. Okay, the second order aerodynamics. Okay, here desired velocity is added, and the proportional gain is added, and then integral control will be added here. The integral control will help to reject the disturbance, unknown disturbance, unmodeled disturbance in the control system. So if you add the integral control in your control system, then the robustness will be increased to some level. So I'd like to recommend you to use the integral control with the small integral gain. Okay. Anyway, we will introduce integral control to remove the disturbance. Okay, the PI control is given. Okay, here the new term is assigned here. The sigma is the integration variable, and the t is the current time. Okay, so the area of theta E propel will be used to correct, to reflect their action, the time history of theta E. Okay, with this controller, for the analysis, aerodynamics can be obtained like this, and then theta dot is designed for the velocity control input, so it will be applied to here. Okay, in the case of, as mentioned before, if your amplifier is set, is determined by using the velocity control input, then we should make the control input as a form of velocity. Okay, so this is a control input. So it will be applied. Then you have this equation: first order, zeroth order, and integration. So we will apply one more time derivative. Then we have second order differential equation. Maybe you are good at the concept of standard, so it will be the 2 zeta omega n. It is corresponding to omega n squared. Like this, we can know that the omega n blah blah, maybe the square root of ki. Zeta will be 2 omega n, so 2 ki and kp. Like this, we can know that if you increase the ki or kp, it will influence the omega n and zeta. Okay, it's not difficult. So we have this equation. Okay. I think if you are good at the concept of a mass spring damper, then I think the kp is corresponding to the b over m, ki is corresponding to k over m. So some factor is increased or decreased. It can be depicted or it can be imagined using the mass spring damper system. Okay, we have the characteristic equation kps ki. Okay, then it's not difficult to obtain the solution S1 or S2 using the factor, using the quadratic formula. Maybe it will be KOP over 2 plus KP square over 4 minus KI. It is KP over 2 minus KP square over 4 minus KI. Okay, maybe it's easy to obtain S1 and S2. Okay, to draw this root in the plane of the complex plane, according to the some variable is varied. This plot will be called as root locus. Okay, maybe if you have listened, if you have studied the control system, in the beginning part, the root locus is suggested how to draw it, how to analyze. Okay. Anyway, it has two variables, so we will determine the Kp as a 20. So let's hold Kp as a 20, and then let's plot the root locus according to the Ki varying. Okay. Okay. First time, Ki is given as 0. So Ki is 0. Then we have this characteristic equation. It can be factored using the s plus 20. So we have two roots, 0 and minus 20. Okay, if you assigned 0 Ki value, then the one pole will be to the 0 origin, and another pole will locate in the minus 20. Okay, let's increase the Ki, a small value. Okay, as Ki increase, okay, in the beginning time, two pole located here, okay, maybe the 0, and then Ki increase, pole will move to the small pole will move to the left, large pole will move to the right. Okay, so roots move toward each other on the real axis of the S-plane, as shown in the left-hand panel in the figure, this figure. Because the roots are real and unequal, the aerodynamics equation is overdamped, is right? Zeta is larger than the 1. Okay, and then the error response is sluggish due to the time constant. It is a slow one, is right? The point near origin will be the slow. So time constant will be the 1 over real pole. So minus 1 over S1 over the exponential corresponding to the slow root. And then Ki is increased, the damping ratio will decrease, and the slow root.
찾은 결과입니다.
I'm sorry. The slow root move left, while the fast root move right. Those are same sentence. So the response will be faster. Okay, the first time, the 0 minus 20 are given as a pole, Ki as a 0. Ki is increased, will move to the left. This one will move to the right. And then, when Ki is set to 100, at the time the two roots meet at the same point, here. For given the Ki as a 100, we have two roots at the minus 10. Okay? Because the S square and the 20S and the 100, it will be factored 1 over 10 square. So we have two roots here. Okay, and the aerodynamics equation is critically damped. So this will be criterion overdamped or underdamped. And the error response has the short 2% settling time. Okay, maybe it will be equal to 0.4, and no overshoot, no oscillation. Okay, here we have two eigenvalue or root close the pole. Okay, and then K increase more, much more. It continues to grow, then damping ratio will be smaller than 1. At that time, the root will vertically off, like this. The complex pole will appear. So complex pole will be the minus 10 plus minus j, Ki minus 100 square root value. Case Okay, the aerodynamics is underdamped, and the response begin to exist or overshoot and oscillation. according to the damping ratio is become smaller. The same, but the settling time is the same, okay? Because it will be proportional to 2 over Kp. It is corresponding to 0.1. So 2% settling time will be the same, 0.4. According to our simple model of PI control, we always choose Kp and Ki for critical damping. Maybe the Ki should be assigned as a Kp squared over 2. It guarantee for the critical damping. Okay. I think the big Kp and the big Ki satisfying this relationship will be better, but hardware has some limitation, so we should consider the hardware limitation. Then we can choose appropriate Kp, and then using this equation we can assign the Ki. Okay. As described above, so there are practical limit. We should consider it. Okay, so this will be the conclusion of this section. Well-designed PI control can be expected to provide better tracking performance than the proportional control. Okay, this single joint motion control will be extended to the n-dimensional robot system. It is called as independent joint control. Many books use this terminology, independent joint control, AJC. So the same controller will be extended to the vector. This will be the vector like this, n-dimensional vector. As the desired is the same, n-dimensional vector. Kp. This gain should be extended to the matrix, diagonal matrix. Okay, the diagonal term can be changed, but for the simplicity, the same diagonal term will appear here, but it can be changed. Kp1, Kp2, Kpn, like this diagonal matrix can be made. Okay, maybe you know that theta E implies the error vector, and then integral is also vector, and the Ki will be the diagonal matrix. Like this, the single joint concept extended to the multiple joint. Okay, section 3.3.3, task space motion control. Okay, we are using the feed port plus feedback control, PI, that is recommended by this textbook. So we will use feed port plus feedback control as a PI. Okay, in the task space, the homogeneous transform XSB, the body frame and effector frame in terms of the S frame. Okay, the configuration of end effector as a function of time will be given in terms of space frame, and then body twist is given by the taking this formula, XSB inverse time XSB time derivative. Then we can determine the matrix form of a body twist. From here we can extract the 6 element to construct body twist. We have dealt with this concept in the chapter 3, so you should review the formula existing in the latter part of chapter 3. And then desired motion is described, XSD is a homogeneous transform, okay, in terms of S frame, space frame. And then the desired twist can be given by using this homogeneous transform, like this. Okay, now we will write down the end effector task space version of a control. The desired twist is given by like this, but it is described in terms of the D frame, is right? So D frame should be changed into the B frame, body frame. So adjoint operator will be used to transform the coordinate frame from D to B. Okay, and then proportional gain matrix, and XE. XE is the belonging to the R6, okay, and the XE integration, and okay, it is corresponding to the position error and the integral error, okay. Okay, let me show you. Let me explain again. The term adjoint XSB inverse XSD times desired twist will bring to the desired twist in terms of body frame. Okay, the feedboard twist in the actual end effector frame. Okay, so the the desired twist will be changed into the body frame, and then if you choose the end effector frame as the desired frame, then it will be identity matrix. So I'm sorry, this is typo. T should be removed. I'm sorry. The body twist, desired twist, will be equal to the body twist. Desired twist will be expressed in the body frame. Okay, I'm sorry. The compilation error XE. Okay, let's assume that. Let's consider the compilation error XE. It is not simple the subtraction, because homogeneous subtraction does not imply anything. So it does not mean the simple subtraction between the XD and the X. Okay, so XE should refer to the twist. Okay, for unit time takes the XB to the XSD. So the XSB inverse XSD and the log transform will provide the 4x4 matrix of XE matrix form. From here, we will extract omega and V from the R6. It can be applied, maybe the zeta and the zeta. It will be applied to here. Okay. For unit time, the twist variation will be assigned as an error, computation error. Okay. One more. This kind of formulation is called as SE3, small SE3 of the body twist. Okay, diagonal term both are same. Okay, the commanded this is the control input, but it cannot be applied to the amplifier joint for the joint control. So we will use kinematic resolution. So the body twist will be equal to body Jacobian and the zeta dot. If you have the inverse of the body Jacobian, then we can get the zeta dot. So this velocity relationship is used to make the joint velocity as a commanded velocity. Okay, so JB and here, it will be task space motion control. Okay, motion control in task space can be defined using other two representation of end effector compilation. Maybe you are good at this kind of if you have the minimal coordinate, such as px and py and pz, and if you know the roll pitch yaw angle of the end effector, at that time we can collect the x using the roll pitch yaw angle and the position 3 vector. Then we can write down the desired roll pitch yaw and the desired xyz, and using this kind of concept vector, we can write down the very simple feedforward plus PD formula. On the other hand, the hybrid configuration case, the remaining PD control is the same, but this notation is a little different. In the previous slide, XE skew-symmetric form is log XSD SB inverse. XSD. The log transform is applied, then we can extract from here like this, omega zeta and v zeta. This will be applied to the previous slide, but in here we will separate the rotation part, orientation part. Okay. So rotation transport and the rotation will be used, and then take a log parameter. Maybe it can be assigned like this, can solve like this. Then position error is applied. This separated six-dimensional value will be applied. On the other hand, the omega and rotation and translation motions are decoupled using the rotation matrix and identity matrix. So the body twist is decoupled in terms of the omega and the p dot. Okay. Okay, let me write down the previous equation. B adjoint xv inverse xsd will be applied to the adjoint map, and the vd and kp xe plus ki 02 xe sigma d sigma. In here, xe, the SE form of the SE is obtained log xsb inverse xsd. Okay, it means the body frame should follow the xd, and then the difference will denote it here. Okay, so xe is xe and this xe is a little different between both. Okay, the left figure, the result of the body twist control. Okay, left side. Okay, this is the initial configuration of end effector. This is a target. So according to time progress, it will approach to the desired posture. Okay, then it shows a little bit natural motion. On the other hand, the decoupled orientation and translation motion, initial condition, and the final configuration. In the case of translation motion, we follow the straight line. Okay, because it was decoupled in calculating the SE. Do you remember the SE? SE will be the log transform, RSB transport, RSD, and PD minus P. Okay, so it belongs to R26. Okay. If you use this kind of decoupled motion, then the position movement will follow a little bit linear. On the other hand, the body twist is used, then the very natural movement, the circular motion appears. So, okay, the end effector velocity is the body twist, and end effector velocity is given by the blah blah. Those equations show, or this formula shows different performance. Okay, in here, the initial condition, this is the x hat, so 0, 1, 0, and the y will be the minus 1, 0, 0, because this is the space frame, and then g is equal the same, and then 1 and 1, so 1, 1, 0 is given by. I'm sorry, it should be given by the 1, 1, 0. I'm sorry. Okay, the feedforward velocity is given by the 0 to compare between the xe notations, and the ki will be the 0. So the very simple proportional control is applied both. Okay, so like this, the figure shows totally different paths followed by the end effector. Okay. The decoupling of linear and angular control in the control law here is visible in the straight line motion. Okay. If you separate like this, then you can make the your control law from here. Then the straight line motion will appear. Okay, let me ask you, the straight line is natural. Human makes use of the straight line motion in your hand. I don't know. I think the left side, the twist motion is more natural. That's my opinion. So if you don't agree with me, then you can make your own theory. Okay? Anyway, the some case, the robot end effector should follow the straight line. Okay. At the time, the decouple, you need to decouple the orientation part and the position part, and then feedforward plus feedback control, PI control, can be used to make the robot motion control. Okay. The next issue will be the chapter 11.4. In that case, we will use the control input as a joint torque. And nowadays, we are using the electric current to mimic the electric the joint torque. Okay. Anyway, I will try to provide the movie lecture movie soon.